Okay. So we are still doing capacitors. Gonna wrap this up. I should have plenty of time to do some homework problems. I've got a couple that I'm planning to do, and if anyone has any requests, please do let me know. Um, you do have homework due tomorrow. You do have a quiz over the weekend. Does anybody have any questions before we get started? Everyone pretty happy? Awesome. Okay. You can go there. You can come over here. No, I didn't mean to do that. Okay, capacitors part 2. Okay, so here's where we were. We had talked about what a capacitor was, how it worked, discussed parallel plate capacitors, got a nice equation for them, and then talked about how you would find the total capacitance of two or more capacitors in series or parallel. Okay, and I wanted to do, and I'm going to start with number 18. I'm going to start with number 18. Let me write down some equations first. So like in series, the equation we had is 1 over C equivalent equals the sum of 1 over Ci. In parallel, we had C equivalent equals just like the sum of Ci. And in general, a parallel plate capacitor has a capacitance of kappa, where that's the dielectric constant, epsilon naught multiplied by the area divided by the distance between the plates. Okay, so those are equations we're going to work with here. So we have a situation where in number 18, they have this one capacitor, parallel plate, but they have filled exactly half of it with a dielectric. So so things that we're told. The distance between these two plates is D. The area of the plates is A. 2A, sorry. 2A. This over here is air, and this has some kappa that is more than 1. So in other words, it's an insulator. And we would like to find the total capacitance of this setup. Okay, sound okay? So what are your thoughts? How would you do this problem? Okay, so we definitely are going to say, okay, well, parallel plate capacitor has a capacitance that looks like that, right? Okay, but how are we going to deal with this kappa? Because half of the kappa is air, which, by the way, has a kappa of 1. And the other half has some other kappa. So how should we deal with that? Split it in half. I like that, because these are really like 2 capacitors. So things that we could start drawing. We could say, okay, well, since those are metal plates, like we could just pretend that they're two capacitors touching. And then we could even kind of say, okay, the wires here probably hook up, the wires here probably hook up. And so instead of this, we could draw it like this. And that would be electrically exactly the same, because everything along this wire is an equipotential, right? And everything along this wire is an equipotential. So it doesn't really matter if you hook the plates together or if you keep them as separate plates. They are electrically connected. Okay. And now looking at this situation, we have now these two capacitors. Are they in parallel or are they in series? Parallel. So let's draw this. So we have a situation like this, right? Where when charge comes in, there we go. You see it? It has to choose one or the other. One kind of hallmark of parallel is you have to have one of those junctions. You like see a T or a cross or something. So these two things are in parallel, which means that we can treat them as two separate capacitors, figure out their capacitance, and then find the equivalent capacitance as if they were in parallel. And so let's do that. So like this guy, I'm going to call it C1, will have a kappa, an epsilon naught. What about its area? Like we said, the area of the entire plate was 2A. So what would you say the area of like 1/2 of that was? A. Awesome. And it's still distance D apart. Okay, and then this side will look the exact same way, except the kappa there is 1, and so we don't really need to include that. Like that. And then the final step, as you guys probably have gotten. So this is kappa epsilon naught A over D plus 1 epsilon naught A over D. Can I factor out the epsilon naught from this sum? What about the area? And the D? Yes, perfect. Okay, so after you do all of that, what you really have is epsilon naught A over D kappa plus 1. And that's the equivalent capacitance of this setup. Is everyone pretty happy with that? Okay, excellent. Sweet. Then let's do the other half of this problem, which is number 17. Where now we have a very similar situation. I have my parallel plate capacitor. The distance between the plates, 2D, the area of the plates, A. But now, and we're going to fill it halfway with a dielectric, but now our dielectric, instead of covering like the left or the right half, will cover the bottom half. And so that's D and that's D. And it's got some kappa that's more than 1. And of course up here we have air. Okay. So we, again, are going to want to figure out the total capacitance of this guy. And again, we're going to want to think of this as two separate capacitors. So we're gonna play this as a capacitor like that, and then another capacitor filled with green stuff. Now, are those capacitors in series or are they in parallel? Series, excellent. Okay, so let's figure out the capacitance of each separate, and then let's add them together. So the capacitance of the top, C1. It's got error, so its kappa is 1. I have an epsilon naught. The area of the plates is A. What about the distance between the plates? What would I put for this particular case? Just D, because I want to pretend that there is a plate in between those. So I'll just have D. And then capacitor 2, that'll be whatever kappa that is, epsilon naught A over the same D. And now specifically to tie them together, now we're going to have to use this equation. So let's do that. Okay, 1 over C total will equal 1 over C1 plus 1 over C2. 1 over C1, that'll be 1 over epsilon naught A over D. C2 looks exactly the same, but with a kappa added. Well, first thing I'm going to do is I'm going to put that D on top. So we have D over epsilon naught A plus D over kappa epsilon naught A. Okay, and again, I'm going to want to factor some stuff out. So what can I factor out? D epsilon naught and A. And so I'm left with 1 there and 1 over kappa there. Okay, is that my total capacitance? No, because I've got to flip it. Okay, so that equals 1 over C total. But now let's flip that. So C total would equal epsilon naught A over D. And this is really nice because we know in general the capacitance should have whatever dimensions of an epsilon naught area over a distance. So I'm very happy to see an epsilon naught area over a distance. And then this other thing, 1 plus 1 over kappa inverse, like that. I don't know if they, and just to work this out, I don't know if they care if you work this out or not. But to work this out, that's kappa plus 1 over kappa to the negative 1. And so that's kappa over kappa plus 1. So you could take this and instead of having what's in that parentheses inversed. But either is mathematically correct. Okay, does that make sense? Kind of happy with that idea? Okay, so that is how you add capacitors in series and in parallel. Any questions about adding capacitors in series or parallel? Everyone pretty happy. Okay, if you guys are happy with that, then let's talk about energy, because that's kind of where we started in this chapter, where we said capacitor is a way to store energy. And so far we've talked about the electric field inside of a capacitor and the shape of the capacitor and how to practically put a capacitor into a circuit. But now let's quantify this energy. And so let's talk about where this energy is coming from. In a capacitor, Okay. So I have a parallel plate capacitor, like so. I'm going to draw it a little bigger just to make some exaggerations. And I'm going to hook it up to a battery with some potential difference across it. And what will happen is, well, let me stick with what's physically going to happen. We're going to have little electrons traveling that way because this the voltage there is low, and so the electrons want to go from a low voltage to a high voltage. And so they travel around, and then they will stick to that plate. And then another one travel around, and it'll stick to that plate. And then another one will travel around and stick to that plate. Is this a sustainable situation where we're just going to keep on sending electrons in and everything's going to be great? No, right? Because electrons don't want to be next to other electrons. So sending the first electron in, very easy. It's happy to go. Second electron, third electron. But as that charge starts to build up, it's harder to put more electrons in there. And it takes more energy to get each electron in there. So we can think about the amount of energy in this capacitor as how much energy it takes for the battery to push the charge onto the capacitor. Does that make sense? Okay. I would like to note, as this happens, that plate becomes negative. This other plate is going to become positive because part of what's happening is the electrons from there are going around like that. So one plate becomes more positive, one plate becomes more negative, and as charge builds, this electric field between the plates gets bigger as well. And that's where we're saying the energy is being stored. So the battery does work to push the electrons onto the plate. Those electrons, the positive and negative charge, create an electric field, and that's what's going to store the energy. That's where the energy is now. It went from the battery to the capacitor in that field. Okay, so let's talk about this. I said work, and that's a good place to start, because work is how energy changes, right? Work is a change in energy. We have energy changing. So really we should be thinking about work when we do this. In particular, if you need to take a charge and push it across your potential difference, that amount of work is equal to Q delta V, not delta U, delta V. Okay, where I dropped the minus sign for a second because I haven't specified if that charge is positive or negative in either of a chart. You know, there's lots of positive and negatives that could be in here. But the amount of energy it takes to move a charge from one potential to another is Q delta V. Noting that across these plates, a potential is growing. Right? As that electric field gets larger, the potential difference gets larger as well. Is that okay? Okay. So what we need to do, what we're going to do is we're going to calculate the amount of work it takes to push charges across a potential difference. So we're going to write this like this. So we're going to say there's some total amount of charge, Q here. We're going to say, and that's the Q, that's a charge on the capacitors. We're going to split that Q up into little chunks, dQ. And we're going to say we've got to push each of those dQs across the potential difference, delta V. This is the charge that goes to the capacitor. This is the charge on the capacitor. I'm sorry, the charge that goes to the capacitor, that's a potential difference of the capacitor. Now, let me ask you another thing. I was about to say, I was going to ask you another thing. Right. The potential difference across the capacitor, does it depend on how much charge is on the capacitor? So if there's an uncharged capacitor, completely empty capacitor, will there be a potential difference across it? Like no. No, okay. But as soon as I start putting charges on it, that's when the potential difference forms, right? So in this case, the potential difference on the capacitor, it's not a constant. We can't take it outside of this integral. It's a function that depends on charge. And luckily, we know what that function is because we have the basic definition of what a capacitor is. It's charge per unit voltage. So we can rearrange this in terms of what we have here to say the charge, boop, boop, boop. No, sorry, wrong one. The voltage, that's what I care about. So the potential difference is the charge over the capacitance, where I can take this Q over C and I can plug it in right there. And that tells me the function that I have, the function how voltage depends on charge. Okay, okay. Let me skip that to the next page. So we're doing this work. It is the integral dq, and this is Q over C, where C is the capacitance. And we're adding more and more charge to the capacitor until we hit some total charge Q. So far, so good? Okay, that capacitance, so the C, that's the capacitance of whatever capacitor we have here. Does that change when you put more or less charge on it? No, right? That's just, you know, kappa epsilon naught A over D. It's independent. An object has capacitance whether it's charged or uncharged, just like a room has volume whether it's full or empty. Okay. So now we are integrating Q dq. And what is the integral of Q dq? Q squared over 2. Yeah, it's just like x dx, right? So 1 over c, Q squared over 2. And we're doing this until we hit the total charge Q. And so this is just going to become total charge on our capacitor squared over 2c. And that is the amount of work being done by the capacitor, which means that's also the amount of potential energy in a capacitor. Since the amount of work being done equals the change in potential energy. And again, I'm dropping the minus sign because it's one of those work being done on a system versus work being done by a system. The capacitor is taking in energy. So you might think of that as negative work versus positive work where it might be giving out energy. But anyway, it looks pretty good. Capacitance, the energy in a capacitor, Q squared over 2C. What sort of units would you put on this? What are the units of energy? Joules. Yeah, so you put a joules on this. And it is a scalar because it is a potential energy. So no direction to that. Now you will see this in a ton of different formats. So since C equals Q over V, you can make all sorts of substitutions to this. So like you can say Q equals C times V, and then this becomes CV squared over 2C, or CV squared over 2. You can, what's the other one? You can get rid of the C by substituting in the Q over V to where the C is. And if you do that, you'll get 1/2 charge times voltage. They're all equivalent. It's not a big deal which one you use. It's just use the one that's convenient. Okay, does that make sense? Okay, so this is the energy you would find in a capacitor, but we wanted way back when to talk about this energy in an electric field, which would be really nice to have because of a lot of reasons. So let's look at how we could think about the energy in that electric field. And I'm going to use this equation to talk about the energy in the electric field because it's convenient for me. So if the energy in my capacitor, which I know is stored in the electric field, is equal to 1/2 C, and that should be really a delta V, but a voltage squared. Well, let's assume that I have a parallel plate capacitor. And we're going to assume I have a parallel plate capacitor and run through this and then say, okay, it must be true for everything. Well, if I have a parallel plate capacitor, I know that the capacitance will be epsilon naught A over D. Okay, useful. And then looking at the voltage, let's draw a picture of our parallel plate capacitor. One plate, a second plate that is parallel to the first plate. Distance between the plates, area of the plates. There will be some potential difference between the plates. That's why that needs to be a delta there. That is equal to the electric field multiplied by the distance it's spread out over. Is that okay? And what is the distance this electric field is spread out over? It's D, right? The distance between the plates. And I don't even have to worry about like calculus because this is a constant electric field. That's the whole joy of the parallel plate capacitor, is that field is constant. So you can just say E times D. Okay, given that, there's my electric field, there's my D. It's squared because my voltage was squared. And let's start breaking this apart. We have 1/2 epsilon naught A E squared. And then notice I'm going to have a D squared on top and 1D on the bottom. So one of those will cancel out. And so I'll end up with 1D on the top. Okay. And now take a look at this A times D. So the A is the area of the plates. The D is the distance between the plates. Looking at that picture I drew of that parallel plate capacitor, what physical quantity would correspond to the area of the plates multiplied by the distance between them? If you took the area of that plate and multiplied it by the distance, what would you get? A volume? Yeah, you get the volume inside the plates, right? Because you're doing length times width times height there. So you really, like, you have this volume inside of there. Sound good? Okay, so this is really 1/2 times the volume inside times the electric field squared. And one thing you could think about that volume is that's where the electric field is. Wherever like the volume between the plates, there exists this constant electric field that fills that volume. So the volume inside of those plates is the same as the volume of the electric field. Okay? Okay. So what you can do at the very end here is to say, if the potential energy of that electric field inside the plates equals 1/2 its volume times the electric field squared, then you can do a energy density, which is useful, which is the total energy divided by the volume. So energy per unit volume, and that'll be the electric field squared divided by 2. Oh, I dropped an epsilon naught in here. There's an epsilon naught in here. Good. With a constant on it. Okay. Okay. This it's going to take us to the end of the semester to actually use this, but we will use this. Remember it when we come back, and we're going to do the same thing for magnetism. Remember it a lot. Sound okay? So if you have an electric field and it's filling some volume, this is the energy density in that electric field. Just so you know, it's got units of joules per meter cubed because it's an energy per unit volume. And I don't think I have anything else to say about that. It's a scalar. Pretty happy? Okay. Well then, that's a good problem. I'm gonna ask you this question. I don't think it's on your homework, but it's a really good question. Let's say I have a battery, and I'm gonna hook it up to 3 capacitors. And I can either hook them up in series or in parallel. So same battery, and same capacitors. So I can hook them up like this, or I can hook them up like this. C1, C2, C3. Okay. So like I say, same battery for both of them, same capacitors for both of them. Only thing different is the geometry of how I hook them up. But I hook them up, I turn them on, charge collects on the capacitors, voltage is spread out across them. I let it sit for a second to let everything hit as maximum voltage as it will. Which setup will have more energy? What do you think? Say again? Let me ask you a different question. In which of these setups would the potential difference across the capacitors be greater? Let me ask you this one. For this one, for C3, what's the potential difference across C3? You guys sure you don't want to say? You said it on Tuesday. No, okay. If the top here is at 6 volts, what's the voltage right there? 6 volts, voltage right there, voltage right here. And across the bottom, so what's the potential difference across that capacitor? 6 volts, same as the voltage across the battery, right? Yeah, so the potential difference on this parallel lines, every potential difference is the same as the battery. Make sense? What about the one in series? It's slower, right? It's lower because you have to add them all up to get to 6 volts. Does that make sense? So for this one, they're the same all across. For this one, they're the same all across. For the one in series, the voltage of 1 plus the voltage 2 plus the voltage of 3 is the voltage of the battery. So it's divided. Okay, so this one has a higher voltage here. And then we go back to our to our equations. Like maybe that one or that one would be a good idea. How does our, if you have the higher voltage, what does that tell you about the energy? It will increase. So this has the more energy because what this allows you is to have the higher voltages. And if you want to think about that in terms of electric fields, all of these capacitors, like capacitor 1 has the same distance between the plates, right? So that means that the electric fields that they're putting out depend on the voltage between the plates and the distance between the plates. Since the distance is the same and one of the voltages is bigger, then that means that there's more energy. So you maximize your voltage, you're maximizing your electric field. Sound reasonable? Okay, excellent. That's a really good one, which brings us to our homework, which we should do a very similar problem to that. Let us find one of them. Is this the one I want? There's one of these that I thought was a really good problem. This is probably one of them. And we got charge, we got potential difference, got more charge. Sorry, just making sure I have the right one. Let's go with number 16. Number 16. Okay, so number 16, we have a battery with voltage V0. We have 2 capacitors. C1 and C2. They go ahead and give us the values of these capacitors in microfarads. Wow, C2 is C2. 5.1 microfarads. And then, oh, look at that. They give us the voltage of the battery. Good. 6.25 volts. Okay. And then they'd like us to find things out about C1 and C2. For example, part A, they ask for the charge in microcoulombs stored on capacitor 1. So they want the charge in microcoulombs on C1. How could we find that out? And you might ask, what equations do we have that involve both charge and capacitance? No, yeah, I think I heard it. C equals. Excellent. Yeah, yeah. Just start out with the basic definition. And I'm not joking that this just like embed this in your head. It's gonna come back a lot. Okay, so the capacitance, which we have what C1 um, is in this equation. It has what we want, Q. What about the potential difference? Can you guys tell me the potential difference after I hook this capacitor up to the battery? 6.25, excellent. So this is going to be the voltage across the battery. Perfect. Okay, so that means if we want the charge, we're going to want to say C times delta V, and that is 1.5 microfarads times 6.25 volts. And luckily they ask us for the answer in microcoulombs, so you don't even have to like do the unit conversion. You can just keep the micro around. And so that'll be how you can figure out the charge. Okay, does that make sense? And if that makes sense, the next question is we're gonna ask for the energy in microjoules stored on capacitor 1. So just to make sure we know, we have the capacitance of capacitor 1, we know the voltage across it, and now we know the charge. And so when they ask us for the energy, we have a few options. Which one should we use? QV? 1/2 QV, that would work. Yeah, and in fact, any of them would work at this point, right? Like we have all of those things. But yeah, 1/2 QV is a good one. Potential energy on capacitor, 1/2 QV. And so that's 1/2 times 9.4 microcoulombs. Our V is the same, 6.25 volts. And luckily they do ask us for the energy in microjoules. So just like keep a hold of this micro and don't stress too much about it. And that'll give you 29.3 microjoules. Okay. After that, they go on and they ask the same questions of C2. They ask for the charge on C2 and they ask for the energy in C2. What voltage would you expect across C2? Same as before. Good. Yeah. So you wouldn't expect the voltage to be any different. Given that the voltage would be the same, would you expect more or less charge on C2? Which one's bigger, C1 or C2? C2. And so if you're multiplying a bigger number by the same voltage, you're going to get more charge, right? Which absolutely should make sense because the whole point of capacitance is the more capacity you have to shove charge on that capacitor without increasing the voltage, that gives you the higher capacity, your capacity to store charge. So yeah, this higher capacitor, not only will you get more charge, but then of course you're going to get more energy as well. So bigger capacitor, bigger charges, bigger energies. Okay. I am completely done with this chapter. Are there any homework problems that y'all want to go over? Because I can move on to the next chapter. I can choose some problems. We did the truly interesting ones already, but let me. Yeah, of course. Since the difference, charging microcoulombs, we kind of did that. Total capacitance, numerical value, total charge. I don't know if I like that. Okay, okay. I might want to do number 10. Number 10 might be interesting. Oh, never mind. I actually want to do number 9. Number 9 is far more interesting. Okay, yeah, let's do number 9. You guys good here? Okay, number 9. We have 4 different circuits where we have hooked up a battery to a capacitor. We put a switch in here just so we can say whether it's turned off or turned on. And that's the first configuration. I'm going to put like an A by it. And then we have the second configuration, same battery, but now we have 2 capacitors. Each one have the same capacitance as the capacitor in the first situation. So all of these are identical capacitors. Third configuration. How many I only have 4, right? Sweet. Third configuration. Battery. 1 capacitor, 2 capacitors, and 3 capacitors. Like so. And fourth configuration. 2 capacitors like this. Oop. Okay. Okay, same battery on each of these things. And these are all identical capacitors. But what we would like to do here is we'd like to rank these circuits from least amount of capacitance, least amount of total capacitance to most amount of total capacitance. Does that make sense? Okay. Let's start with most. B. I like B because when you're in parallel, you're just adding up those capacitances, right? So B looks pretty good. I'm going to put most B over here. Okay. What about least? Close. I like D. I like D over here. And let's do some math to kind of show that. Yeah. So A just has the 1, right? And I guess you're looking at D and saying, hey, it has 2. Okay. Let's do some math. Let's in particular let's find the equivalent capacitance of D, just to kind of prove this to ourselves. So for D, we have it's in series. So 1 over C equivalent is going to be 1 over C1 plus 1 over C2. Now this is pretty easy because they're both C0, right? So they're both the same. So we could just go ahead and put a C0 there. Okay, we have 1 over C0 plus 1 over C0, so that's really 2 over C0. That's not an epsilon naught, that's a C0. And then, of course, we need to invert it. Last step. So it looks like our capacitance, when we added a capacitor in series, has actually halved. And let's talk about this a little bit in terms of this problem we just did. where we found when we added capacitors in parallel, that really increased their ability to hold energy. Like overall, the amount of energy in that circuit went way up. But when we had them in series, that decreased the amount of voltage each one had, which meant that decreased the electric field across each of them, which meant that decreased the amount of energy they were holding. Does that make sense? So adding capacitors in series does not increase the amount of energy your circuit has. It actually decreases the amount of energy your circuit can hold. Whereas adding them in parallel increases the amount of energy. Sound good? Which is why D has a lower capacitance than A, even though D has more capacitors than A. So far, so good. All right. Last one, C. What do you guys think about this one? Yeah. Say again? More than A? Yes, but I would have to do the math on this one to be sure of that. Because, so it's definitely more than D, right? Because these two capacitors in parallel are going to have more capacitance than one capacitor by itself. So it's more than D. But whether or not it's more than A, it is. But let's go ahead and do the math on that one to make sure. Okay. So looking at this, can we say anything in this circuit is truly in series? That everything that goes through one of the elements, all of it goes through the second element. No, okay. Okay, so we're not going to do anything in series at first. How about parallel? Is anything truly in parallel? Those two. Okay, so we're going to take these two, and we're going to say C equivalent equals C naught plus C naught, because they're in parallel. So that's 2 C naught. And then we'll redraw our thing where we have C naught and 2 C naught like that. And now these guys are in series, right? Okay, so we can say 1 over C equivalent will equal 1 over C naught plus 1 over 2 C naught. Well, what's 1 whole plus 1 half? 1 1/2 or 3 halves? Okay, so we have 3 halves times C naught. And of course, we got to flip it at the end. So our C equivalent is 2/3 C naught, which, as you guys correctly told me, is more than 1/2 C naught. So yeah, C would be over there. Not as much as B, where B would just be 2 C naught, right? But more than just 1 C naught. That was a good problem. I like that problem. Okay. I got one more from here. We could go in the back. Okay. I got one more. Number 10 that we could do, or I could just go on to the next chapter. Number 10. Okay. The next chapter is pretty straightforward too. You'll like that one as well. Okay, so number 10, we're gonna have a circuit with a bunch of capacitors in series. So 1, 2, 3. So we got C1, C2, C3. And I'm going to have a V1. So I'm going to measure the voltages. I'm going to have my voltmeter. I'm going to measure the voltage right there, and right there. Okay. Now they're going to give us the values of these capacitors. Oh, they're going to give us the values of 2 of these capacitors. Give me a second. Okay, whatever. The third one is an unknown. And we are told that the charge stored on these capacitors is 2.5 micro, not farads, but coulombs. Now, do I need to specify which capacitor I'm talking about when I say the charge stored on the capacitor? And given that these 3 capacitors are in series, yeah, okay, no, because remember, so on Tuesday we talked about capacitors in series and what's the same between them and what's different. And we said, well, I couldn't really say what the voltage on each capacitor is, just that it adds up to the voltage across the battery. But I do know that the charge on each capacitor has to be the same, because as charge is going through that circuit, it's going to the same charge is going to hit each capacitor. So when we say the charge is 2.5 microcoulombs, that means the charge on each capacitor separately. Okay. Okay. This is I like this problem a lot. First question asks for an equation to express the capacitance of any capacitor in terms of Q and delta V. So what's the equation of capacitance that includes Q and delta V? You got it. Q over delta V. Check. Now we're going to take this formula, we're going to apply it to capacitor 1 and find the potential difference across capacitor 1. So part B, C1 equals Q1 over delta V, and this potential difference is going to be the potential between V1 and V2. So we're going to call that delta V12. And this works great. So since we're looking for delta V12, that's delta V12 equals Q over C1. Straightforward. They don't even, I assume at some point they're going to ask for numbers, but you could plug in numbers at this point and you could find that. Okay. Next question. And this is where I really start to like this. Now they want us to express the potential delta V12 through the potentials V1, V2, and through potentials V1 and V2, where V1 and V2 are potentials measured at 0.1 and 0.2. So if you were going to write an equation of delta V12 with just V2 and V1 in it, what would that be? Go with the obvious answer. V2 minus V1. And hopefully that makes sense, right? Like if you measure a particular voltage at V1 and you measure a particular voltage at V2, then the voltage across capacitor 1 should be what those 2 voltages are subtracted, right? Like that's just what it should be. Excellent. Okay, now they're going to tell us that V1 is 9 volts. So like this side of the battery here, 9 volts. V1, 9 volts. And they would like us to calculate V2. So V1 is, where are we? If V1 is 9 volts, what's V2? And so now we're combining we're combining part B, and we're combining part C. So V2 is going to be delta V minus V1. V2 equals delta V minus V1 from part C. And delta V12 is Q over C1. So this is Q over C1 minus V1. And I feel I threw a minus sign out somewhere. But I'm gonna ignore that minus sign in a second. Oh, I see where it is. Oh, I'll do it their way. This is 1, this is 2. Don't worry about it. We'll talk about it in chapter in 2 weeks. Okay, this looks great. I'm happy with this. Let me switch this around. V1 minus delta V12, V1 minus Q over C1. Mainly, I just need my answer to be positive. And at this point, you really are just plugging in numbers. So you have 2.5 microcoulombs divided by 2.1 microfarads. And notice that the micros just cancel out, so you don't even need to think about it that hard. Okay, and you get 7.81. And let's talk a little bit about our minus signs, because I did pull a bit of a fast one there, where I switched those two. If we're starting off on the positive edge of the battery at 9 volts. Once we get to the negative edge of the battery, we need to be at 0 volts, right? So across each capacitor, we expect the voltage to go lower and lower and lower. So we need to start at 9 volts and subtract off whatever the change is. And now we're at V2, we're at 7.81 volts here. And we're going to go across the next capacitor, and we're going to drop off another chunk. And then whatever's left over, that'll be whatever's dropped off the third capacitor. Okay, meaning that if we want V3 will be V2. Let me just make sure I'm saying it right. V3 will be V2. Yep, V2 minus the voltage across capacitor 2. And let's pop back up to the picture so you can all confirm. You start at V2, you subtract the voltage across capacitor 2 to get to V3. Okay. Okay. And as for part E, that's what they want you to do. So you start with V2. Can we use that same equation, charge over capacitance for voltage, just like we did in like part B? I saw a nod. Charge over capacitance. And can we use the same charge for capacitor 2 as we did for capacitor 1? Yes, excellent. 2.5 microcoulombs over 4.2 microfarads. And so at this point, we'll have 7.2 volts. Okay, so we started here with 9 volts. We dropped down to 7.81 volts here. We're at 7.2 volts there. When we get to the other side of C3, what will our voltage be? 0. So that means we know just by the process of elimination that the voltage across C3 is going to be 7.2. Okay. Okay. All of you guys are nodding. So this is great. Unless there's some, are there any, I really should ask, are there any questions in particular that anybody wants to ask about this chapter? Yeah. Okay. Then let me talk for just 2 minutes about what we're going to do next week, so we have a good starting place next week, and we'll be good after that. So we're actually building up to circuits and like direct current circuits, and putting like a light bulb and capacitor in a series in a circuit together. And so the next thing we're going to look at is we're going to be looking at how current works. And we've talked about how, okay, charge is going to go around the wire, but we're going to start really like laying down some rules for it, and putting some equations to it so we can say exactly how charge makes its way around a conductor. We're also going to talk about resistors. And so resistors are anything that resists current. And so we're going to talk about how things resist current, like what about a material would stop current. And then we're going to quantify that down into, okay, I have an element that is a resistor. And then we're going to talk about, are we going to talk about that? And then we're going to talk about how things like temperature might affect resistance. But that's pretty much all we're going to do next week too. I think you like next week's. It'll be pretty straightforward, just like this week's. But is everyone kind of happy with that? Okay, then let's go ahead and call it. You do have homework due tomorrow and a quiz over the weekend. Online people, are you guys good? I haven't heard anything from the online people.